Now that we've seen how to use motion diagrams to understand what an object is doing when it's in motion, we can extend that idea into full motion graphs. And for all of the graphs that we're going to deal with, we're going to put time along the x-axis. It's going to be our independent variable. And so time will continue to tick away at a steady pace along the x-axis, and that's why it's independent. It won't be affected by anything else. And then we'll look at different things along the y-axis that are changing as time goes along. And the first one that we're going to look at, as you can see from the title of the note, is displacement. So these are going to be displacement time graphs, but they're also in a way tracking position. So regardless of whether you think of it as position time graph or a displacement time graph is really up to you and not essential to understanding this concept. But if we look more closely at this first example, as we said, we've put time along the x-axis, it's independent, and d for displacement, or you can think of it as position, along the y-axis. And we don't need to worry about specific numbers in this case. We're just going to look at generally what's happening to the object in motion. One thing that's handy to label right away is the origin point. Because you'll notice that the actual line that describes the object's motion does not start from that origin point, but it does have an important meaning. If this is a position time graph or displacement time graph, I need to measure those positions as starting from some point of reference. That is what the origin is representing. That's our point of reference. So if I say that my position is 24 meters east, what I really mean is it's 24 meters east of some particular point in space that I have called my reference point. And so this is the actual starting point for the object's motion, and it would be some number of meters away from the original reference point. We just don't need specific numbers in this case to at least see what's going on. In the first section of line, we have a line that's slanting upwards from the point where it crosses the y-axis. So we need to think about what that means. Well, if the line is going upwards, it means d is increasing, which means your position is increasing its number of meters away from the reference point. So if you're increasing the number of meters you are away from your reference point, that means you're moving away. So for that entire section that's slanting upwards, the object must be moving away, and that's why the number of meters between it and the reference point is increasing. But then there's a section where it flattens off. It becomes horizontal. Well, if it's becoming horizontal, that means for that entire section, it's actually not changing at all how far away it is from the reference point. So if there's this long stretch of time going by when you're not changing how many meters from your reference point you are, that must be because you're not moving at all. We could also say you're at rest. So on a DT graph, anytime we see a horizontal line, or a flat line if you want to call it that, it means the object's at rest, it's not moving. And then in the last section, we see that it is doing the opposite of what the first section did. Now the line is slanting downwards. Or in other words, the number of meters between the thing moving and the reference point is decreasing. So if you're decreasing the number of meters between you and the reference point, it means you're kind of closing that distance. Or in other words, you're coming towards the reference point. So you're moving back towards the reference point in that case. And I'll also just be a little bit more specific. You're doing it a little bit faster than you moved away. And we know that you're doing it faster because you're able to cover a greater amount of distance in an even shorter amount of time. And so if you're able to cover a great amount of distance in a shorter amount of time, it means you've done something faster. And that should hopefully make a little bit of logical sense, but mathematically what we see happen on the graph is that we get a steeper line. When we see a steeper line on the graph, on a dt graph specifically, it means an object moving faster than it was before. So down below, we can talk about the meaning of what we really see happen here. Now that we've summarized that on our graph specifically, let's talk about what these different things mean. So the direction of the slope. Well, we've already seen that the slope could go up this way in what we'd call a positive slope, or it could go down in this direction, what we'd call a negative slope. But we can be more specific than that and talk about what the object is really doing. So when we have a positive slope, we saw that that meant you were moving away from the reference point. And if it was negative, it means you're moving towards. But I just talked a little bit about the steepness as well. So positive and negative slope doesn't tell us everything about what's going on. We can also look at how steep the slope is. And so, for example, we could have very steep slopes up or steep slopes coming down. And whether they're steep slopes going up or going down, that steepness just means that you're moving very fast. If we see what I can call more shallow slopes, slopes that don't go up nearly as quickly or down nearly as quickly, again, that word I used was shallow slopes, another just word for less steep. Well, that's telling you the opposite. That's telling you the object is moving fairly slowly, because you're not increasing your number of meters very much as a certain amount of time goes by. And if you're not able to cover a lot of ground as time goes by, it's because you're moving slowly. If you're able to cover a lot of ground as time goes by, it's because you're moving fast. And covering a lot of ground will create a steep slope. Covering not so much ground will create a shallow slope. So we can use that logic now to look at a graph that's a little more complicated and try and determine what's happening at various points in time. And so here we've got different letters marking out different instances in time along this graph. And so if we look at point A, what's happening is it's curving upwards. And so it's curving from an area that has a less steep slope. Whoopsie. Curving from an area that has a less steep slope to an area that has a more steep slope. And you can see from those little pieces of slope that I've highlighted there that it clearly is getting more steep. So if you're getting more steep, that means you're actually increasing your speed, because steeper things are moving faster. And so if this thing is increasing its speed, then more specifically we would say that it's accelerating. That's what the curving upwards tells us, and the fact that it's moving upwards or moving up the graph also tells us that it's moving away. Because not only are the slopes getting steeper, they're all positive slopes in the area around A. So it's accelerating away from us. At B, on either side, the slope stays fairly constant. And so right around point B, we've got a fairly constant slope. And so at B, we can say that it just continues moving away, because we know that it's still a positive slope. But we can say more specifically, it's doing it with, and I'll say roughly, constant velocity. At point C, we see the slope just before point C has a certain steepness, and then after point C, it's starting to flatten out a little bit more. And so we're going from more steep to less steep. Anytime that steepness is changing, that means the speed is changing. So more steep means a faster speed, less steep is a slower speed. So this is actually getting slower. So as you see around point C, it starts to curve and get less steep. It's actually slowing down. So it slows down, but all of the slopes are still positive. They haven't turned back and started to point downwards at all. They're just less steep. So it slows down, but it's still moving away. That's really important not to forget. Then finally, by the time we get to D, really on both sides, it's gone pretty much completely flat. And as we saw before, when it goes completely flat, that's when it's finally comes, or it has come to a stop. And that fits together nicely with some of the other pieces because we can see C, which comes right before that, is it gradually slowing down, and so it should make some nice, smooth, connected sense that at D it's coming to a stop. So there's a little bit of stuff you can try in the bottom part of that first page in your note, and I'll talk about that more in class. A little bit of stuff we can try with a motion detector ourselves that will actually graph out these DT graphs in real time on the screen for you. And we can play around with those a little bit when we get to that in class. If we've seen that the steepness of the graph has a lot to do with the speed of the object, well, we should start to look more mathematically at what that means. Well, steepness in math is specifically referred to as the slope. So mathematically, why does the slope seem to be connected to the speed of the object? Well, if we go back to the basic definition for what slope really means, it's rise over run. Or another way to say that is the change in your y variable divided by the change in your x variable. But we can be more specific than that in our case, because we're not just dealing with y's and x's in general. We now have specific things that those y and x axes are measuring. So along the y-axis, it's not just the change in the y variable, it's specifically the change in position, or in other words, your displacement. The x-axis is referring to some change in time. Well, when we take displacement and divide it by a certain amount of time that's gone by, we already know what the definition for that is. It's velocity. That's really what we found. And that's why the steepness had so much to do with the speed of the object, because really we're finding its velocity. Now, we should be careful. Technically, what we found when we just do this simple division is what I sometimes call VAV, or average velocity. And that's what's stated in your note below. So what we found is that the slope of a line on a DT graph is actually equal to the average velocity of the object. And we can see through a little bit of unit analysis that that works out. And so unit analysis is just a way for us to look at the individual units that make up some larger quantity and see how they relate mathematically to each other to create units for that larger quantity. So, in our case, what we just saw is that our formula is delta D, or in other words, displacement divided by delta T. So when we do unit analysis, I like to start often by writing out the variables that are included in our calculation. But now, just to the side of it, what I'm going to do is use some square brackets to just indicate that anything inside of those square brackets is a unit. And so the unit for displacement, in our case, is simply going to be meters. In other cases, it could be kilometers or centimeters, but the most common one we'll use is meters. And I just keep it in square brackets so that you know it's not a variable called m, it's a unit that means meters. And time could be measured in lots of different things, but we're going to most often use seconds. And so we've got a unit of meters divided by a unit of seconds, and those units divide just the same way that numbers would. So we get an overall final unit of something called meters divided by seconds, or in other words, meters per second. And that's the same units as velocity. So not only does our intuition and our knowledge of slope tell us that this should connect to velocity, the units tell us the exact same story as well. Now, so far, we've only seen examples where we are calculating the slope of a straight line. But not every dt graph has a straight line on it. In fact, the previous example that had A, B, C, and D in it had curves all over it. So what if that dt graph does have a curve? Can we still find the slope of a curve? And there are many important ways that you can do this exactly and mathematically, but really you need calculus to do it exactly. So instead, what we do is just try and find something called the instantaneous velocity, and we can use an approximation method called the tangent line method to do that. So if we want to find the object's velocity at a particular moment along the curve, we just need to find the slope of its tangent line at that point. So let's take a look at what that means. Here we have our graph with a curve on it, and there's a specific point where that big dark block is right there that we are trying to find its specific slope. Now, if we just look in the immediate area, just on either side of that point, if we were to zoom way, way in close on that graph, we would see that right around that point, the slope is doing essentially what I've just highlighted in green. Now, at other points, though, of course, the slope is much steeper. At other points later, it's much flatter. But right around that point, it is going in that green highlighted direction that I first put in. This dotted line that's also already on your page is how you would draw a tangent line at that point. A tangent line is one big long straight line that extends what the slope is around that point in either direction. So when I first drew in the green line around that point, you can see that it represents the slope right in the area around it. If I then extend that green line straight in both directions, I get what's called a tangent line. And the reason I want to extend it now is because when it's extended, I can then try and identify any two other points on it. So maybe I can identify easily a point that's over here using its x and y coordinates, and I identify another point that's over here by finding its x and y coordinates. And then once I have those x and y coordinates, I can put those into the slope formula that we've already used a little bit in this note and that you saw back in grade 9 and 10 math. And I can use the points on the tangent line to find the slope, even though those points aren't actually on the dt graph's curve itself. We're going to see lots of cases of how we use this in class, and I'll go through some more detailed examples of exactly how we draw these tangent lines as accurately as possible. For now, though, just try and understand the basic concept of how we draw these tangent lines and why we use them for curved graphs.